Perfect. Thank you very much for the invitation. Hi, everyone. My name is Yuyan. I'm a PhD student at McGill University at Milo, and today I'll be presenting our work on Open Insect, which was published at NeurIPS 2025 Dataset and Benchmark Track. So to begin my presentation, I would first like to give you a very brief overview of the background and the motivation of this benchmark. So I'll first start by introducing what is biodiversity, which is essentially the variability of life on Earth. And it can be measured at various levels, for example, genetic diversity, species abundance, and biodiversity monitoring itself is very important for us to evaluate conservation efforts, track changes, and inform policies. So for our work, we focus on insect and build a dataset and benchmark to evaluate unknown insect species detection in biodiversity monitoring, because actually to a great approximation, all species are insects, or to be more precise, on 2/3 of species that have already been described on Earth are insects. And they have very important roles in different ecosystems or pollinators. They're also prey to other species, for example, birds and bats. Um, so Unfortunately, we've been observing a decline in insect abundance over the year. We see decline in a lot of orders of insects, including Lepidoptera. So the order over here, which is the order of moth and butterfly, and these are the species we focus on in our data set and benchmark. Even though a lot of insect populations are declining, we actually know very little about them, and we don't know much like how the population are changing. And it's only until very recently that we have started a large-scale and long-term monitoring system to study insects, and with the help of these automated monitoring system of camera traps and machine learning to do image-based species recognition. So here is one example of such a system deployed in the wild. And there is a machine learning pipeline to do this job and to help us extract information in a much faster manner. But unfortunately, this actually poses a great challenge for a machine learning species level classifier, because actually 80% of the insect species are still undescribed, which means regardless how much data we can gather to train our model, we can, at our best effort, only train a model to recognize 20% of the species. So, which means our classifier cannot give us a very useful information, because, well, of 80% of species, it would just give us a wrong answer. So this is precisely the task of open set recognition, and why this is very important for biodiversity monitoring. So the task of open set recognition is to accurately classify test samples from the closed set and detect test samples from the open set. To put it in a more formal way, we can think open set recognition as a binary problem where you have a real value and you pick a threshold to decide on for all the samples that give you score greater than threshold, you consider the sample is unknown or from the open set. And for the rest, you would consider it as the closed set, and the model should classify it correctly. So for the existing benchmark on open set recognition, there is a great work, this great work called OpenOD, which consists of various data sets and benchmark to test open set recognition. However, these data sets are much smaller, at a much smaller scale. So they're built on top of very generic image data sets, for example, MNet C for 10, C for 100, or Tiny ImageNet. So these data sets, they're usually at a coarser grain, and also they don't have that many classes, which is very different in the scenario of biodiversity monitoring. So as I'll show about the data distribution in a second, you'll see how the data distribution in our data set is very different from the current benchmarks. So in order to test the current open set recognition methods, and to see whether the current open set recognition methods can be applied to actually detect unknown species in the wild, we present Open Insect, which is a large-scale and fine-grained dataset to evaluate unknown species detection. And we built our dataset for 3 geographic regions. We also split our data into the closed set, the open set, and the auxiliary dataset, and I'll go into details in a few seconds. I put a QR code here, which links to our project page. So our dataset, our code, and the paper are all available from the link. So for the three geographic regions, we focus on Northeast and North America, Western Europe, and Central America, where they present different levels of biodiversity, with Central America being the most biodiverse one. But unfortunately, we have the least information in this area. Um, so for our data set, we have the closed set. As I just mentioned, the closed set is just the training set we'll be using to train the model. So the model should accurately classify the species within this closed set. And for the closed set, we built our closed set on top of another insect data set, which is called Amy GBIF. So the images in this data set are curated from GBIF, which stands for the Global Biodiversity Information Facility. So it's basically a data infrastructure for us to gather a lot of biodiversity data. And in this case, it will be images from Citizen Science Platform and museum collections. And then for the open set, we have three different OpenSet types to make it conform to the OpenSet recognition literature, because you will usually have the near outer distribution samples where those things the classes in those samples look more similar to the things in the closed set, and they'll also have a far outer distribution samples where the samples look more different, so they should be easier to recognize. So we built our open set with three levels of difficulty. One is the local open set, where we pick our open set samples from the surrounding area of the closed set samples. So the color here indicates biomes, which is the climate and also the vegetation type in this region. So we pick the samples in the surrounding area. And as you can see by the color coded here, they have very similar biome to the closed set region, meaning that the species there are very likely to be much more similar to the closed set, which poses a great challenge for the machine learning model to recognize very similar looking species. So here is an example of the species in our data set. So for the local open set, a lot of species are actually very similar to the closed set samples. As you can see, a lot of them are just one hop or two hop away from the closed sets, and they look extremely similar to each other. And for a much for another easier version, we have a non-local open set. So we get the species of the non-local open set from Australia. As you can see, the color here are very different from all the other three regions. So the species are also likely to look way more different. A lot of species are actually three hops away from the example, so they're still moth, but they're already like more different from the closed set. And then finally, we have, which should be the easiest split of the open set, is the non-moth open set, where we have these insects. They're still insects, so they're likely to show up on the camera trap systems. Um, we still want our model to exclude them, but they're way more different compared to the closed sets over here. Okay, so for our benchmark, what we did is we evaluated 38 open set recognition methods. 36 of them are existing method, and the other two are some very simple baseline we proposed, and we included in the benchmark as well. So following existing literature, we classified the 38 OpenStat recognition methods into three categories, being post-hoc, training regularization, and training with auxiliary data. And I'll go into details just in a few seconds. And then for the metrics we used standard metrics to evaluate the OpenSet recognition methods. So for the closed-set performance, we use accuracy, and for the OpenSet performance, we use the area under the receiver and operator curve, because this is essentially a binary problem, and we want to see the performance of the model and across all thresholds. Okay, so I'm gonna first give a few examples of OpenSet recognition methods. under different categories. So for the post-hoc methods, we are given a pre-trained model, so no training is required, as the name suggested. We'll have an output of the model, and then we'll convert the output of the model to some open set recognition score. And then based on the score, we pick a threshold and decide whether whether the sample belongs to the open set or the closed set. And a baseline of such approach is the maximum softmax probability, which should be the most intuitive one because we can just take the softmax, which is you get the score for free when you're doing classification, and then you pick the the maximum of the softmax score. And if the maximum is very big, it's very likely the model is more confident on the sample, and the sample is more likely to belong to the closed set. And then if the score is small, very likely the model is not very confident on the sample, and the sample may be from the open set, which has not been seen by the model during training. Another type of method that has been proposed is training regularization. So this method requires training. You can start with either a neural network trained from scratch or already pre-trained classifier. And then you train it with some other loss function for some epochs. And then you can combine this approach usually with some other post-hoc method to actually give you an open set recognition score at the end. So an example of training time regularization will be the logic norm regularization. So instead of training the model with the classic cross entropy, we want to normalize the logic at training time to make sure the logic does not increase too much during training. Um, so the third type of the method we evaluated is training with auxiliary data. So the previous type of the training method, we only need the closed set for training. And then for this type of method, training with auxiliary data, we would also have another set, an auxiliary data set, and then we train the model together with the closed set and the auxiliary data set. So the intuition behind this is we hope that our auxiliary data set will be similar to the open set, which we don't have access to at training time, but maybe the model can learn something from the auxiliary data set that can improve the performance of open set recognition. So an example of this will be the energy score. So the energy score is one of the post-hoc method that has shown a strong performance on open set recognition. So if we do have access to some auxiliary data set over here, or denoted as the train out in this equation over here, we can try to train the model with this auxiliary data set by pushing the in-distribution data to have an energy score closer to mn over here, which is a constant you set before training. And then for the auxiliary data, you want push the energy score of the auxiliary data. In this case, they're also different from the classes in the closed set data to be closer to the M out over here. So essentially, you want to delineate the two distributions of the in-distribution data versus the out-of-distribution data so that things in the closed set and the things in the open set will have very different energy score at the end. So when at test time you apply this energy score to the samples from different classes will have more different values. So another very trivial example we included in the benchmark is if we have auxiliary data set, we can simply train two classification heads, and one classification head only with a closed set, and the other one you either treat the classes of auxiliary data set separately, or you just treat them as one single class, just the other or the novel classes, and to optimize the model together with the cross entropy of the closed sets and the closed set plus the additional classes to let the model learn more from the auxiliary data set. So here are the very high level presentations of the benchmark we proposed. So we plotted these box plot to summarize all the 38 methods and how they perform on our open insect dataset. So as we can see, the local open set species are more difficult to detect. This is more or less intuitive because we have already shown that the samples in the local data set look very similar to the samples in the closed data set. We also observed that the best performing method can achieve over 85% of area under the curve. So this shows a very strong potential for automating species discovery, but clearly there is still a room for improvement. Actually, a large room for improvement because even within the insect classes, the local open set species perform much worse compared to the other two categories, meaning that we for the open set recognition methods, there is still a room to push the score to push the score to a much higher score. And for the post-hoc methods, we have observed that the baseline of the post-hoc method, which is a maximum softmax probability, and some other variant of this actually still remain a very strong baseline in this fine-grained case. So, okay, there are a lot of numbers over here, and for sure, no one want to read it. During this presentation, but I'll just give a very quick overview of it. So the bold number over here indicates the best performing method under different categories. So we can see the maximum softmax probability and also the temperature scale, which is this a scaled version of this uh, maximum softmax probability, still remain a very strong baseline, and they can achieve the best performance for many data splits. And then we also see this RP MSP, which is another scaled version of the MSP score, also achieve very good performance under the post hoc method category. And then for the methods required training, we actually do not see a large improvement if we train the models with training time regularization of these six methods we've tested over here. And we do see some improvement if we train the model with auxiliary data. And the auxiliary data, I'm going to talk about our ablations study on auxiliary data in a moment. But the takeaway over here is if we train the model with auxiliary data, we actually need to be careful about the selection of auxiliary data. And the auxiliary data needs to be similar to the open set in order for it to be useful. So that giant table I presented just now is built on top of the large scale data set I just presented. But we also want to know whether the method will actually work in the wild, because all the species we have in that large scale data set are already known species. We're just splitting them into different categories and using the open sets to simulate the actual unknown species will be seen during biodiversity monitoring. So in order to test whether the benchmark is a very good indicator of the performance in the wild, we also have this much smaller scale data set in open insect. The data set was collected on the Barro Colorado Island in Panama. So indicated over here as OBCI. So we have 197 moss images and 133 open set species. So this is at a much smaller scale compared to the previous data set I presented. However, 59 species in this data set are very likely to be new to science. They show a much larger DNA divergence, like so the DNA divergence, if it's greater than 2, it's usually a good cutoff for species identification. So these species actually represent new species in the wild, and we want to see whether the performance of different open set recognition methods on this much smaller scale data set is consistent with what we observe in the giant table I just presented. So here we plotted the performance of of the model on the BCI dataset versus the performance of the model on the Central America split of the local open set. So as we can see, there is a positive correlation between these two methods, indicating that if the method performed well on the large open insight benchmark, it's very likely to also perform well on detecting unknown species actually in the wild. So another question we answered in our paper is about explainability. Um, so it's actually a very important question to answer, especially when we want to apply the model in the wild and convince biologists that machine learning can greatly facilitate their work in detecting new species. And one common concern from we got from biologists is, can models just simply rely on background instead of actually focusing on the fine-grained species level features to detect whether the species is known or unknown. Because if the model is only relying on the background and the result is not very trustworthy for biologists, and it's likely to break if we apply it to another monitoring system. So in order to do so, we did an ablation study when we mask the moth in the photo, and we also masked the background to see the change in performance of the two types, like moth masked background mask versus the original image. So what we observe over here is when we mask the moth in the photo, we see the area on the rock curve drop to 46%. So 50% is random performance. So it's like the open set recognition performance is near random, meaning that the model is actually relying on the moth to make a decision instead of the background. If we mask the background, the performance drops slightly, 4%, but not a lot. And also our classifier is also relying on the moth itself to make classification, because the accuracy dropped just to 1.63%. And then finally, we did ablation studies on auxiliary data, as I just mentioned, because the previous benchmark of the Open OED benchmark fixed the auxiliary data for all training for all different closed set and open set they tested. They used Tiny ImageNet. We curate different auxiliary data for different regions. And what we notice is that if we use our auxiliary data, we see an improvement, especially on the local open set. So we would suggest, if people are looking for auxiliary data to train to improve open set recognition performance, people really need to curate a data that's relevant to the setting instead of fixing one auxiliary data for all type of training and for all type of closed set and open set. And then we also did another ablation study on pre-trained weights. So we use the BioClip pre-trained weights. So BioClip is a recently developed foundation model for species classification. And in practice, a lot of biologists, when they're using machine learning to do species classification, they wouldn't train everything from scratch. So we want to see if we want to use an already pre-trained foundation model to do species classification, whether it will harm or improve open set recognition performance. Because for a benchmark, we actually train all models from scratch for the post-hoc methods, and for the other training method, we fine-tune it from the model trained from scratch. So we use the bug clip weights and also the classic pre-trained weights we usually use in image classification, which is the ImageNet 1K. So we compare the two different types of pre-trained weights, and we see that bug clip, which is the bug clip weight, which can be considered more relevant to our task compared to ImageNet 1K, shows improvement on open set recognition. So, um, if biologists want to train the model from a pre-trained foundation model of species recognition, this can actually improve the open set recognition performance. Yeah, that's it for my presentation. Thank you very much. And I put the QR code again here for our project page, and people can scan it to get access to the paper, the code, and the dataset.